Hello, it's Keith here, and this is lesson 26 of the platform-specific series of my 68000 assembly tutorials. We looked at hardware sprites on the NeoGeo last time, and we learned the basics of creating individual sprites and combining them together to make chained larger sprites. Now, as I said before, the NeoGeo is a bit different to most console systems because it doesn't actually have a dedicated tile map. Now, what we can do, however, is we can use that chaining ability of the sprites to build a kind of simulated tile map, and that's exactly what the NeoGeo games do when they need to create multi-layered tile maps. So today we're going to learn how to chain those sprites together and build a simple tile map. So first of all, let's actually see the code running that we're going to be using today. So here's my example code just starting up here. And if we just fast forward this a bit. So here you can see a tile map, and I'm using the scaling options here to make it smaller. It looks like it's getting bigger, but as I've said before, the NeoGeo can't scale sprites up, it can only scale them down. So it's actually getting it's actually reducing in the amount it's shrunk rather than actually getting larger, so to speak. Now you can see actually the tile map is having a bit of a wrapping effect when it gets too big for the screen, so there's a bit of a glitch there, but the code is, you know, it's not really a proper code that you'd use in a real example. It's just I wanted to show the scaling effect in practice. So if we were really going to scale the game as you make a zooming in and out effect, then we would want to hide some of the right hand side of the tile map when the tile map became too big for the visible screen. Now, when it comes to the sprites we're going to use for today's episode, these are, as usual, converted with my AccuSprite editor. These are some 8x8 tiles that I'm using in some of my other tutorials that are coming up, but I've scaled them up to 16x16 because that is the sprite size of the NeoGeo. Now, if you want to use them as an 8x8 tile map, you can do that. You just need to scale down by 50%, so you need to scale your tiles up when you save them in the export, and we can do that here. We just go to NeoGeo here, save sprites, and this is part of my other sprites in the example we looked at before. So we're just exporting these sprites and then we're using them in today's example. Okay, so how do we actually build a tile map on a system with no tiles? Well, with the NeoGeo, it's not actually as bad as you'd expect. I was sort of pleasantly surprised by how relatively easy it is. So essentially, if you remember the NeoGeo, the sprites are limited to 16 pixels wide. They're 16 by 16 square, but a hardware sprite, as a term within the NeoGeo, can be made up of 32 vertical tiles. So each one is a pattern that's 16 by 16, but those 32 tiles will all move together as a single object within that sprite. Now, we can then take a second sprite and chain that to the first one, and then those two will move as one continuous object. Now, the reason that the tiles are separated from the concept of sprites is that the system can have up to 380 sprites on screen, 96 on a single line, but as I say, the tiles vertically kind of don't use up that allocation, so to speak. So the sprite is only the 16 pixel wide element. So we can have something the full height of the screen with a single sprite. We need approximately 20 sprites to fill the width of the screen because each of one of those can be the full height of the screen, and then we would just chain them together. So if you think of our sprite layout for our screen as being like this, then what we're effectively going to do is we're going to have the first sprite as a sort of anchor, and that's going to have its vertical tiles. We're then going to chain a second sprite to that anchor, and it's going to have the same number of vertical tiles because the height is always the same for all of the chained objects, and then we'll keep chaining more and more sprites along until they fill the width of the screen. And the exact number of sprites we'll need to fill the width of the screen will depend on the scaling option that we're using. I believe it's 20 sprites if we're using the normal scale, 16 pixels wide, but if we're going smaller, we're going to need more sprites. So that's kind of the mechanism we're going to be working in. So what we're going to do in today's example is we're going to have some code that's going to programmatically build up the initial tile map with all of the sprites combined together. And then we're going to have another bit of code that will tweak that tile map, changing the individual tile numbers so that we can build up a picture that you saw, kind of a fake Mario style platformer. Just quickly show you the very small example down here. So we've got kind of some grass here and a little hero maybe here and some blocks. So it's a very, very crude example of a kind of play field, but you know, a realistic kind of thing you might want to do with a tile map that the NeoGeo wouldn't normally allow. So we're going to have some code to allow us to tweak the tile map after we've built it up, and then we've got some example code that's going to do the scaling. So first of all, let's just stop that so that we can see it without that zooming. So here is our sort of basic tile map. Now these are effectively 8 by 8 here, so there's a 50% scale down. Remember, we can't technically scale up, we can only scale down, so it's a shrinking effect, not a zooming effect. So we've got our kind of grassy areas here and our blocks. Now this here, this giant Chibico here, towering over everything, this is done by the fixed layer, remember, which is really designed for text. You can see the text here as well. So they aren't scaling, it's these sprites that are scaling. And let's have a look at the code that's doing that job. So we're using this code here, and the start of the code we're going to look at today starts just here. So the first stage is a loop that's going to build up the tile map, and that goes all the way down to here. So this is the first part. This sets up the sprites. It sets some initial values which aren't going to be the final tile numbers, but just a sort of generic starting point. We set the initial scale here. I've put in 3 options. We've got enough width for a 50% scale, so it's going to be too big if we were doing it at full size, if we were using the 16 by 16. This is sort of designed for an 8 by 8 tile size because it's scaling down. As I say, you could move this down to, I think it's about 20 if you were using no scaling. But 37 is the correct number of horizontal sprites for a scaled down tile map, I believe. So that's what we're going to be using here. And then once we've created our tile map here, we're going to load in the initial layout, which you just saw from this data here. You can see these 3s are the kind of ground area. You can then see these 2s here are the sort of grassy areas. And these 4s, these are the blocks. And then 5 here is our kind of hero character here with the sword. Now, the sprites within the ROM file start at hexadecimal 200C. That's because the other sprites are used by our other characters that we saw in the previous example. It's the same ROM file we're using today. So we're going to have to add 200C to these values here when we actually set that tile map. But that's not the first stage. The first stage is going to be just setting up the sprites and chaining them together. So we're going to load some default values just here. So we're going to use 2 memory addresses in VRAM, and this is because of the way the data is set up. If you remember last time, there are 2 addresses we need to change. We need to change hexadecimal 8000 in VRAM to set the shrink, the YPOS offset by 200 there, and the XPOS offset by another 200. And there's 2 bytes per tile. Now there's 32 tiles per sprite, so that's 64 bytes per sprite. And these start at hexadecimal 0. Sprite 1 would be hexadecimal 40. So the first one is the tile number effectively. There's a little bit more detail because there's a few extra bytes of tile number in the second address, but we're not going to go into that. It's just a simple example. But the second address basically holds the palette for our purposes today. We're not going to worry about flipping and things. So that's what we're going to be working with. So we need to set these addresses at the 8000 range and these addresses at the 0 range, and that's why we've got these 2 defined here. We're setting our scale in D5. Now the vertical scale is defined by the anchor sprite, the first sprite, but the horizontal scale is defined by every single sprite. So it's perfectly viable for us to have this at full width and this at half width for a kind of stretching effect. And I think this could be useful because if you look at the way that the scaling options work on the sprites, we have a full 8 bits of vertical stretching flexibility, but just 4 bits of horizontal. So you might need to kind of do some betweening where some of the tiles are being scaled down and some of them aren't, to basically simulate more bits of detail if you were looking to do a nice smooth scaling option. But anyway, it's completely outside of what we're doing today, but I just wanted to point out that the fact that we can scale these horizontal parts separately might be quite useful. So anyway, really that's just why we're defining at this stage the scaling option. That's because it does have to be set for every single sprite, not just for the anchor. Then we're defining the width. We're defining this as 37 here in D4, and the height, the number of tiles per sprite, in D2. Of course, D4 is the number of sprites because, as I say, we need 1 sprite per strip, vertical strip. So that's the initial data we're setting here. Now the anchor sprite we create just once. The rest of the sprites in our tile map are of course these chain sprites. So let's start creating that anchor. So we're using hexadecimal 3C quadruple 0 here to select the VRAM address we want to change, and 3C 0002 to write the new value. So first of all, we're using D7 here to select the first attribute, and then we're setting the shrink from D5. We're then adding hexadecimal 200. because this is effectively moving us from that first attribute at 8,000 to 8,200 here. And then we're setting the height in tiles. Now the height in tiles usually goes from 1 to 16 as a number of tiles, but there's a special option if we set 33. This tells it to keep filling tiles, looping around until the entire screen is full. And that explains to us why if we just remove that infinite loop from here and run again. And so you can see I've paused it here, and you can see these tiles are being repeated many times for the entire height of the screen. And that's what setting this option to 33 does. It's a special one-time sort of exception to the rules. And what it does is it tells the system to make the sprite draw on the entire height of the screen, even if the tile numbers need to keep looping. So that's what we're doing there. So we're setting that and the Y position here. The Y position is being set to F8, which is the top of the screen. It starts from the bottom, so F8 is the top of the screen. We're setting the X position here. We're setting it to 4. And before we write the X position, we're adding another hexadecimal 200 here. So we've added that twice. Now, we've finished the first anchor sprite here. So we're resetting D7 by subtracting hexadecimal 400, these two 200s together, so that D7 is back to the first position in the sprite. Because although we've done the only anchor sprite, we're going to use basically the same kind of code to do the chain sprites, just with a few different settings. Okay, now we're going into our main loop. So we're now going to add all of the tiles to that sprite that we've just created. So what we're doing here is we are moving D6 this time to the right address. D6 starts at 0. So we are starting at tile number 0 effectively here. So we're now writing to these areas here. So we're going to be setting tile numbers and tile palettes. And that's exactly what we can see here. So we're loading in the tile we're going to show, and we're going to show hexadecimal 2010, and I can't remember which one of these tiles it is. Maybe it's that square one, but we never actually see it because we're going to redefine it as soon as the actual structure of the sprites chained together is created. So we're just writing a sort of starting value here, a generic starting value. We're then incrementing by 1 the address we're writing to, selecting that new address, and then we're setting to use palette 1. We're always using palette 1 in this simple example, so we're only using 16 colors for our tile map. Okay, now we loop around because that's just done a single tile, but remember we need to do lots of tiles. We're doing 27 tiles here using D2. We've pushed D2 into D3 here, and then we're using D3 as a loop counter, so we're creating that here. Now that's actually going to, thinking about it, that's actually going to run to 28 because it will run for 0 as well. It only stops when it gets to -1, so we're doing a 38 by 28 tile map in this example. Okay, so that's our loop there. So we've created our tiles now. So now we've done the first anchor sprite and all of its vertical tiles. We now need to do the chained sprite that combines to the anchor sprite. Now, as I said before in the last lesson, chained sprites can only chain to the previous sprites. We have to use consecutive sprites here. So the next sprite is going to be the first in the chain. So what we're doing here is we've got some code here that is going to effectively remove all the bottom bits of the address that we used to set the attributes of the tiles. We're removing the bottom bits and we're effectively adding 64. So this effectively resets us to the start of the next tile. So we will have gone from 0, 0, 0 up to something maybe like 28 or something. But then those bits will be wiped out. So we go back to 0 and then we add the equivalent of 64 hexadecimal 40. So we're just resetting back to the alignment for the next sprite tile attributes in this kind of order here. So we'll have gone to hexadecimal 40 now, effectively the first time this is run. So that's reset D6 for the next loop of this part. We're now incrementing the sprite because we're going to use the next sprite as a chained sprite. And that's what we do now. So we're writing the shrink again, but only the horizontal part will have any effect. The vertical part will be ignored. We're then writing a Y position here, but again, we're setting it to 0, but it's ignored. It's only this chain bit that's going to have an effect. This chain bit will override everything else. It's 4 here. So this is setting the sprite to be chained to the last one. The X position we're writing is 0, but it really has no effect. And then we're just subtracting again to reset for the next sprite. Now we're jumping all the way back up here for the next loop in the tile loop. So this is just filling in the tiles for that chain sprite, and we just keep repeating until we've done all the chain sprites. So at this point we now have a valid tile map. So we can just prove this if I just put a infinite loop in here. So that's the tile map before we set it up, and yes, it was using that square block effect. So our TileMap now works, and what we're doing next is we're actually filling it in with something a bit prettier to look at. So I've defined this grid here of a tile map with just a simple landscape and a few bits of eye candy there, so something nice to look at. And what we're doing here is we are setting the X and Y position to 0. We're loading in the tile map. We're reading in a byte from the tile map. We are adding it to 200C, which is the position in the ROM file of the first sprite of our tile graphics. So that would be the address of this in that ROM. And then we're using a function called setTile. We'll have a look at that in just a second. And then we're just looping around until we've completed the width and the height of our tile map there. So, you know, nothing too exciting there. So really, it's this setTile function that's doing all of the work. So what this setTile function here is doing is it's patching in the new tile numbers into the attributes of the tile sprites. So if you remember, the tile address here is what we're going to be changing. And so we need to work out which sprite we want to change depending on the X position, because remember each vertical strip is a different sprite, and we need to work out which tile number within that sprite we want to change based on the Y position. And if you think about it, each sprite is 64 bytes separate from the last one in terms of these addresses, and each address is 2 wide because the tile palette is the second address after the first one. So this gives us the effect of what we're doing is we're multiplying the X position by 64 and the Y position by 2, and once we do this, this will be the address of the tile number that we actually want to change to set the tile that we are specifying in D1 and D2 here. So we just call setTile with D1 as the X pos and D2 as the Y pos, and then we set D0 to be the new tile number. We call this function, it does all the work for us. Pretty straightforward. So that's how we can set a tile quickly. Now, if we wanted to scroll the tile map, of course, we just need to move that anchor sprite around, but I didn't really want to do that. I thought it would be not particularly interesting. So instead, what I did next was I started scaling. So if we look here, we've got this scaling routine, and this is, again, pretty straightforward. Now, it's not enough to just change the anchor sprite, because we actually need to change all of the sprites. So all I'm doing here is I'm setting D6 to hexadecimal 8000. Now if we look at hexadecimal 8000 here, that is of course the shrink. So what we're going to need to do to scale our tile map is go through the shrinks of all of the sprites that make up the tile map and write a new value to them. So we're starting at hexadecimal 110, which is setting the X and Y to pretty much the minimum, and then we're just updating all of those. We are kicking the watchdog a few times. We've got this pause command here, which is very boring, just a simple crude delay there, just to slow things down so we can see what's happening. And then we are just adding 110 to our scale, and we are just jumping back up here again. Now we've got to check here just to check when we've gone over the limit, because this top nibble has no function for the scale, so we're just resetting everything when we get there. But this is just effectively setting all of the sprite scales in one go. If you don't know what that kick watchdog does, it's a system function of the NeoGeo, because it's a arcade piece of hardware. It's basically got a kind of crash detect. If the game doesn't tell the operating system, hey, I'm still running okay, then the operating system will hard reset the game. So if we disable this, we'll probably find our game just keeps hard rebooting over and over again. So we've just put that in because this is an infinite loop and we needed to make sure that didn't happen. So anyway, that's a basic introduction to how we can use the sprites as a tile map here. Now, basically, as I say, NeoGeo is capable of up to 96 sprites on a horizontal line. That's a sort of physical limit of the graphics hardware. As I say, there's 380 sprites on screen, but if there's more than that on a line, then it's going to start glitching. This means effectively we could theoretically have 4 layers of tile maps, but that would only leave 16 sprites for the game, so we probably wouldn't want to do that. But anyway, theoretically speaking, that's what we're working with. As I say, I think the hardware, while a little bit odd, is pretty nice. You know, it worked a lot better than I expected. I originally just started messing with this. I wasn't sure it was going to be easy enough for me to do a tutorial, but it's turned out pretty well. So anyway, hope you found this interesting. Please like and subscribe if you have, because I'm sure we'll be coming back to some more NeoGeo stuff later, and we're going to be looking at a wide variety of other systems, both 68000 and otherwise. Thanks for watching today anyway, and goodbye. If you enjoyed today's lesson, please check out my website. We've got tutorials, source code and development tools for 6502, 68000 and Z80 systems, and a lot more systems coming in the future. We're going to be covering the 8086 and the ARM and a few other things as well going forwards. And if you've liked this lesson, if you've got questions, comments or suggestions on how it could be made better, please consider signing up to my forum. It's free, of course, and you can come along here and you can make suggestions, you can ask questions. And if you've got assembly projects you're working on, please let us know what they are. Maybe show off a few screenshots, tell us what things you've found interesting or what tricks you've come up with, because we'd love to know about it. Anyway, thanks for watching today and goodbye.